Hello everyone, I hope you are fine. My name is Saad and I'm here to present the paper titled Learning Domain Knowledge for Automated Security Administration. It's written by me and Simon Parkinson, and we are from University of Huddersfield. Right, so every organization nowadays is facing security threats exposed by their IT infrastructure. And there is a proactive need to defend against these threats, to protect your client, to protect your businesses, to protect your data confidentiality. That requires expert knowledge of the latest threats and mitigation techniques. But the problem is, security expert knowledge is in short supply. It might not be available 24/7. It can get quite expensive if you hire experts, and it definitely requires a significant amount of manual effort to understand and implement the security controls. So we thought it would be of great value for both experts and non-experts if we can automatically gather security expert knowledge and then utilize it to improve security of the machines. So our proposed solution is a fully automated solution that uses data mining and automated planning techniques on security event logs. Now, event logs are a powerful source of knowledge. They are referred as the gold mine of knowledge, as they contain every record of user, application, system, network activities. And they contain all type of activities, whether they are authorized or unauthorized. Traditionally, event logs have been used for several purposes, like failure prediction, like troubleshooting, like tracing, step-by-step tracking of events. But we are using these event logs to mine the knowledge they contain. So our solution has two components. The first one acquires the knowledge, and the other one helps in the deliberation process of that knowledge. So for the knowledge acquisition, we have developed an unsupervised knowledge learning techniques. It first generates correlation rules, which are then combined and ordered based on a temporal metric, and then we use them to produce cause and effect relationships. Those relationships, this is for the utilization part, those relationships are then encoded into a PDDL-based domain model, which is then used by LPG algorithm to determine the course of action on previously unseen machines. For the first step, we need to prepare the data we acquire from a machine that is presumably configured by an expert, by a security expert. So the first step is to acquire those event logs. Then we need to remove routine and benign events them, as they can create a snowball effect. As we go through different stages of the process, it can create a snowball effect and essentially ruin the accuracy of the entire process. And after removing those events, we prepare an object-based model, which is basically a comma-separated objects found in each event. We're going to feed this model into association rule mining technique, and to do that, we need to calculate the support. Now, we are calculating the support in an automated manner. Traditionally, users define the support, but we have devised a way so that we can calculate the support in an automated manner. And to do that, what we do is we gather all objects found in all events, we calculate their frequency, and we create object-based frequency distribution. And on that distribution, we apply two-sample Kolmogorov-Smirnov test to determine normality. If that distribution is not normal, that means there are certain objects that were involved in triggering more events than others. And it is evident by the current literature that when you have frequent events, they are usually the routine events. And routine events might not be very relevant for our security knowledge mining, so we need to remove them. So if the distribution is not normal, we take the minimum frequency and we divide it by the sum of all frequencies to calculate the minimum support, and then we take the average frequency and divide it by the sum to calculate the maximum support. But if the distribution is normal, the frequency of all events are relatively similar, so we take the minimum frequency divided by sum to calculate the minimum support, and then we take the maximum frequency divided by the sum to calculate the maximum support value. The confidence value is always kept at 100%, as we need to find the most interesting rules. So now that we have the object-based model that we prepared in the last stage, we have support value, we have confidence value. Now we can use a priori algorithm to generate object-based rules. These rules are then converted into event-based rules by mapping them onto the original event log dataset. This is done using Pearson correlation. And then, after creating the event-based rules, we combine all those events that have the same effect. That means all those events led to a same goal, led to same activity. So we have combined them and then we order them based on their timestamps. After that, we use FCI algorithm, fast causal inference algorithm, to determine the causal strength to extract a more reliable knowledge. Now that we have all relationship, we store them in a database, and from that database, we generate a PDDL based domain action model. So essentially, we encode all rules into the domain actions, and then we assign an accumulative weight to each action to know the strength, to know the confidence, to know the reliability of that relationship. This accumulative weight is calculated by how many times a certain relationship has appeared over different datasets, what is its temporal accuracy, what is the causal strength, causal rank of this relationship. So we use all that to determine the accumulative weight. After that, we take the vulnerable machine, we extract all of its events, and we use them to construct the initial state of the problem instance. So initial state is essentially the current state of all events in a vulnerable machine. The goal state is kept empty. I know it's not very common to keep the goal state empty, and it can be mind-boggling to have an empty goal state. But the problem is the goal state is completely unknown because we cannot determine or even predict beforehand what actions need to be scheduled for the vulnerable machine. Plus, there is no way to determine the set of all or even one missing security control in the target machine. We cannot determine that. So that's the reason we have kept the goal state empty. And along with that, we have used the maximization metric, optimization metric, so that we select as many actions as we can in the plan trace. So this is the example of a domain action. As you can see, it is a relationship between the event 4720 and the event 4732, and you can also find the list of all objects you need to perform this action as the list of parameters. And we also have the accumulative weight, which is increased every time an action is selected. The next is the example of a problem instance. As you can see, we have extracted all objects from the vulnerable machine. All events will form the initial state. The goal state is empty, and we have applied the maximization metric. After we have the domain action model and the problem instance, we use the LPG planner, which is local search for planning algorithm, to determine the action plan. In this case, the action plan would be suboptimal due to the empty goal state. Gives a lot of information that is required by the user to improve their security. And as the action plan can be a bit difficult for the novice users, we created another plan parsing tool to improve the readability of the action plan. So here's an example of the action plan. So here you can see that a malicious user logged in. He tried to escalate his access privileges. Malicious user was found by the administrator and then removed. So this can provide a lot of information for the novice user, as the solution will automatically determine what happened and how to resolve it. For the evaluation process, the first thing we did, we selected 21 event logs from different machines that have been configured by experts. Then we generated the automated plan, and we used the same event logs to generate the manual domain models. After that, we selected a vulnerable machine, we extracted the problem instance, and we used that problem instance with both automated and manual domain models to extract the plan. Those plans are then compared, which is essentially the comparison of human expert knowledge and the automated expert knowledge acquired by our proposed solution. We perform the comparison to determine the accuracy and performance. Here are the results. As you can see, we have achieved a reasonable accuracy within a reasonable time. C is always above 70, and the time is quite short as compared to the time that's taken by an expert to manually build a domain model. That usually takes a lot of time. Thank you very much for listening.